we wanted to understand something like 1 over r, the sum over chi mod q, q of size r, of so it's the sum is over primitive characters. This was going to be a bound in the Bombieri-Vinogradov theorem, and we wanted to take the worst possible case here, so the max over r up to something like root x over log x to some power. Maybe I ended up calling it d last time. And then we made the following observation, that if you had, instead of having one sum over primes, if you had a bilinear sum over a of size a, so let's say this squiggly thing is going to mean that a is between capital A and twice capital A, let's say, and then a sum over b of size capital B, and then you had a sum over characters with q of size r. And then if you had something like alpha A, beta B, chi AB, right? So this is the object to which we use the large sieve, and we proved that this was bounded by something like, give or take some powers of log, some power k. And then we had a bound which was something like square root of xr plus maybe x over r plus something like x over root a plus x over root b. Right? And this term is good so long as r is less than root x over some large power of log. This is good so long as r is at least some power of log. And these two terms are also okay, provided a and b are at least some power of log, some large power of log. Okay? Then the next step was to obtain a decomposition of this type where I can replace lambda n by bilinear forms where both variables are not too small, right? And this, we used the following trick. We wrote zeta primed over zeta. We introduced something like, first we subtracted some over basically n up to some p is what I think I called it last time, right? And then added back the sum over n up to p, lambda n over n to the s. And then this part I multiplied by 1, which I wrote as 1 minus zeta of s times some Dirichlet polynomial m of s plus zeta of s m of s. Right? And then these guys are basically counting primes that are all larger than p. So this times that gave one type 2 sum. So it's so those coefficients will be a bilinear form in which both variables are large, larger than p in this case and larger than m in this case. Okay? And then this quantity times zeta primed over zeta gave me something like, so this guy gave me something like minus zeta prime times m, right? Multiplying this with that. And then also from here you get something like minus zeta of s, m of s, and then this guy, n up to p, lambda n over n to the s. Right? And these three terms here we call the type 1 sums. Okay? And the feature of the type 1 sums is that either they are just short sums, which I can estimate trivially, or they are short sums multiplied by something like zeta or zeta prime. So the coefficients are either 1 or something nice like log n. And those sums are over long ranges, because I think of capital P and M being of size a small power of x, like x to the 1/10, say. Okay? So type 1 sums were easy. So last time I think we gave a bound which was less than maybe, let's say, x to the 0.99, something like this. Right? All of them we could bound by this. Choosing some simple choice of P and M, like P equals M is x to the 1/10. Okay? And then the type 2 sums, So that's this guy times that guy, right? So formally we do have something like a sum over A of some size A and B of some size B. There is really this condition that AB should be no more than x, right? And then some coefficients alpha A, beta B times chi AB. So let's say this is just like lambda of A if A is bigger than P, the term coming from this guy. And then this one you can think of as, 1 minus the sum over D divides B, D less than M, mu of D. Right? Something that's 0 initially all the way up to M, and then it's something non-zero beyond that, but bounded by divisor type functions. Is this good? And then what we realized was that if I ignore the condition that AB is less than or equal to x, right? Just think of A of size capital A and B of size capital B with some product of A and B going up to roughly of size x, maybe 2x. Then the large sieve estimate would be good enough. It's fine, provided R is bigger than log x to some power D, to some power. Okay. So, and the reason is that because these terms alpha A and beta B, they are 0 if A is small or if B is small, so therefore I would gain a square root of A and a square root of B, and I'm gaining some power of x in those cases. I can assume that A is at least as large as P, B is at least as large as M. So these are both larger than some power of x. That's good. So now the last step that we have to do is to just get rid of this this way in which the two variables are linked together by the product AB being at most x. And I want to make them, and I want to just remove this condition. Okay? So at the very end of the lecture, Emmanuel just discussed the same problem as well. You're thinking of a hyperbola, and you look at the points near the hyperbola, maybe divide them into small enough intervals so that you can just replace the hyperbola by small boxes. And then you can remove this condition there. Okay? So if you're just going to save some powers of log, you can just split A into intervals from A to A plus A over log A to, so replace this by intervals like A to A plus A over log A to the 100 or something like that, right? And then count in intervals of that type and then see what the corresponding interval for B should be. Okay? So that's one way to do it. another thing, so the bottom line is that this is kind of just a technicality, and there are many, many ways of getting around this technicality. So this way of splitting into short intervals is one way of getting rid of the technicality. Let me just say one more way of getting rid of the technicality, which has to do with Perron's formula. Again, don't worry about this literally. Think of some smooth version of Perron's formula if you have to, if you don't want to worry about technicalities involved in making this quantitative. But just recall that you can understand whether something is, let's say if I integrate on some line to the right of 0, and if I look at something like x over ab to the s, then I can pick up 1 if ab is less than s, and 0 otherwise. Right? And here C is something just positive. You might worry a little bit because this integral is not really absolutely convergent, okay? But one thing that Demetrius discussed in his lectures was that you can make these kinds of things quantitative by truncating at some big point capital T, and then this will be equal to 1 plus some error that you can essentially explicitly write down. And roughly speaking, you should think of this error as being inversely proportional to t. So roughly like 1 over t. This is not exactly correct. You should look at what your notes from Demetrius's lectures for what you should write down here. Or if you don't care too much, think of putting in a smooth function here, which is going to decrease much more rapidly than this 1 over s, and then justifying any of this would be very easy. Okay? So again, this means that if you want to understand things with an error of saving some large powers of log x, you might just be content with taking t to be some large power of log x to some large power d, let's say, right? And then this c, we will choose fairly close to 0. C might just be something like 1 over log x, let's say. So positive, but very, very close to 0, so that the size of this object, even if a and b are small, it's only of size 1. Right? So what have I gained here? I have expressed this condition that ab is less than or equal to x by some integral. So replacing by, an integral is like introducing some more harmonics, right? And the measure of the thing that I've introduced, well, this t goes up to some power of log x, but it's all weighted by this 1 over s, right? So maybe you really only have to worry about the range of s, which is very, very small, right? Maybe if I choose c to be like log x, this guy, if I just take absolute values everywhere, is no more than log x in size, right? Maybe I can be even more precise. Maybe it's no more than log x in size, right? Okay, so whatever it is, by introducing something which in size is no more than log x, I can distinguish this condition of whether something is less than 1 or bigger than or bigger than x, less than x or bigger than x. Okay, so at the cost of just powers of log, I can distinguish AB less than or equal to x. Right? Or what does it mean? So everywhere that I see, if I have this condition AB less than x, I can replace it by an integral over a suitable region, and then I would have x to the s divided by AB to the s, and now the two things are separated. It's alpha A over A to the s, beta B over B to the s, and then I can use the large sieve as though the two variables were not linked to each other. Is this good? And if you carry it out, you will lose maybe 1 or 2 logs more, and then everything else will be okay. So the upshot is that separating AB can be done with a very small price. Very cheaply. Okay. Any questions on the proof so far? Okay. Okay, so now if I put everything together, I'm almost done with my proof. I have the right estimate that I want for that. So we are okay for Bombieri-Vinogradov unless R is really small, R is less than some power of log x. Right? Okay. And the only place that came up was this term here, x over r, and you're not going to gain anything here if r is extremely small. Right? The large sieve is something which is powerful when you're averaging over more and more characters. When you have a small number of characters, you can't really expect the large sieve to say anything non-trivial. Okay? But now in this case, we can go back and use directly the Siegel-Wolfish theorem. So this was covered in Dimitri's lectures. You can say it in a couple of different ways. So either directly we know that psi x qa minus psi x over phi q is bounded by something like, let me say x e to the minus c root log x. Provided q is less than log x to some power. Right? Or I have the same kind of bound for psi x chi if chi is not the principal character, right? Then I have some suitable bound for this, maybe bounded by x e to the minus c root log x. Again, provided that q is suitably small. Okay. So if I just use this bound, then the small values of r are under control as well. Right? I've saved arbitrarily many powers of log over the trivial bound, and then I can use this for q up to some arbitrarily large power of log, and then that's enough. Okay? So let me say a couple of more things about this, reminding you about what was going on in this Siegel-Wolfish theorem. So So the proof was like the proof in the prime number theorem. Well, actually, Dimitris gave a slightly different way of formulating this proof. But the idea in the usual way is that you have a zero-free region for zeta and L functions. And the usual zero-free region would be something like the region sigma bigger than 1 minus some constant divided by log of qt has no zeros, okay, except for what could be a Siegel zero, except for a Siegel zero, which is a real zero beta of a quadratic character. Okay, so in how Dimitris did it, you looked at the distance between the Möbius function and some character times n to the it, right? And you could get a lower bound for that distance in terms of the distance between 1 and the character squared times n to the it. And if the character happens to be a quadratic character, then chi squared is itself just the principal character, and those two functions are exactly the same. So that distance is not big, and therefore you have a problem with writing that proof. So there are a few related points to keep in mind here. The Siegel zeros are very rare. I mean, they don't exist, so that's certainly one meaning of the word very rare. But what it means also is that, you know, if I look at characters with if q goes up to some point capital Q, and if I replace this by capital Q, then there's at most 1 0 in the interval of the slide of all the L functions in that region. So it's extremely rare. And also we have Siegel's theorem that even when they exist, you can say that beta is bigger than 1 minus some constant depending on epsilon divided by q to the epsilon. And I think that this was something that maybe Zeb and Benny covered in one of the tutorials as well. Right? You didn't mention the zeros. So you did it as a lower bound for L1 chi, right? So maybe it was covered as a lower bound for L1 chi, also in Dimitris's lectures, right? But this is equal to that by basically the mean value theorem. Okay? So now, okay, where this constant is ineffective and this epsilon can be chosen, you know, to be anything positive, right? And this going up to c epsilon over q to the epsilon is the source of this n. You could choose n to be anything you want. N you should think of as like 1 over epsilon. Okay? So that's the reason for this range of applicability in the Siegel-Waldfisch theorem, right? And this, so you know, you might worry a little bit here that as we've presented it, this is also ineffective. So there will be a constant here. X needs to be larger than some constant depending on m for all of this to work. And that constant would be ineffective. Okay? Okay, so to summarize, we've given a proof of Bombieri-Vinogradov, but maybe we want to reflect a little bit on some aspects of the proof to understand what exactly is going on, right? And how it meshes with this Siegel zeros type question. Okay. Before I do that, let me make one more point so that you can see how this ties up with what I first started out with, which is the Brun-Tishmarsh theorem, right, on getting upper bounds for the number of primes. So one other exercise that you can think of is that, okay, so suppose, you know, the usual zero-free region is very good, provided q is not too big, like e to the c root log x, okay? So you can get everything under control, but except for this one bad Siegel 0 case. Okay? So suppose suppose Q is a modulus for which there is a Siegel 0 for the real character chi mod Q. Right? So in this case, you can take the effect of the Siegel 0 in your formula for primes, and you would get something like psi x q a being given by the main term x over phi q, but minus something arising from the Siegel 0 character. So you can explicitly identify this, and there will be a term here which would be like chi of a that comes in here. Okay? So, well, this chi is the same as this chi here, the bad Siegel 0 character, right? So, this means that what the Siegel 0 is doing is that instead of the primes being evenly distributed in all arithmetic progressions, which is what we want on average for Bombieri-Vinogradov, or which we'd like to say for every individual progression on GRH, you have this funny situation where the residue classes A for which chi A is 1, so that will be half the reduced residue classes mod Q. Those guys get very few primes. These two terms will roughly cancel out. Think of beta as being very close to 1. Okay? And then the terms for which chi A is minus 1, the two terms will reinforce each other, and you will get twice as many primes. Okay? So the Siegel 0 situation is like an alternative model distribution of primes. Half the residue classes get twice the primes. And then half of them get approximately 0 times the primes. Their fair share of primes. Okay? At least for a long time. Eventually, of course, once this beta is less than 1, if x is incredibly large, this will go away. But it won't go away for a long, long time. Okay? So that, again, is the heart of what this uniformity is about, understanding when you revert to this equidistribution of primes and progressions, but initially for a while they may not look equidistributed, possibly. Okay? And now you can see again that this twice the number of primes is kind of interesting because we had the Brun-Tishmarsh theorem which says that the number of primes in a progression cannot be more than twice the expected number, right? You know, there was that log x over q that you have to worry about, but think of x as being very, very large, like at least q to the 1 million. Okay? And so you can see that in the Brun-Tishmarsh theorem, if you can replace the 2 there by 1.99, you would be very happy. You would get rid of this Siegel 0 situation as well. Okay? So this is another case. So there are lots of constants that appear in analytic number theory, but some constants are important and some constants are not. So this 2 in Brun-Tishmarsh is a very important constant. It would be nice to improve that. Okay, so there's a bunch of different things connected with the problem of Siegel zeros. It's affecting the equidistribution of primes and progressions, and therefore it also features in our proof of Bombieri-Vinogradov. Some version of Siegel-Wolfish allows us to complete Bombieri-Vinogradov as I wrote down. Right? That's the story so far. But let me make a few more related points connected to this. You might ask, you know, suppose I want to sum over progressions moduli q. Let's say they are between size, let's say, q and 2q, right? And then I want to take the max of the sum psi xqa minus minus the main term x over phi q, right? And then I want to try to prove some kind of Bombieri-Vinogradov theorem for this, again with q going up to something like root x over log x to some power, right? Bounded by x over log x to the b. Okay? So this is the Bombieri-Vinogradov theorem. The only thing that I've done is, instead of having q go up to capital Q, I'm going to make q be of size capital Q, between capital Q and twice capital Q, right? One might think that if I do this, then maybe I'm not going to run into this Siegel 0 difficulty, right? Because all my moduli are large, okay? So I should just be using this kind of large sieve where this modulus R is always going to be large. Okay? So is that true or false? Sorry? So, well, but maybe it's better to first identify why the proof would not work if I just tried to do this. So my question is really, you know, if I try to decompose this, can I somehow restrict myself to characters, right, whose moduli is always going to be large? Therefore, I can use the large sieve in a very favorable way and not have to worry about the Siegel-Wallfisch thing at all. Or am I always going to be forced to deal with characters of small conductor as well?
The large sieve uses like primitive characters.
The large sieve uses primitive characters. So whenever I have these characters here, I have to, you know, figure out whether they're primitive or not, right? I'll have to sum over the, and if it's not primitive, I'm actually dealing with a character of maybe a potentially very small modulus, which is inducing that character, that imprimitive character, right? So that was one of our first steps in the proof of Bombieri-Vinogradov. We wrote this as a sum over characters, and then we converted it to a sum over primitive characters, and then we went ahead with that, right? And in passing to primitive characters, I would have to look at all divisors of Q, right? And then potentially I might then land up with a character to a small modulus which has a Siegel 0, right? So you can reflect here on, well, have to deal with pass to primitive characters in this argument. And okay, so there's some, you know, and this leads back to Siegel zeros, right? Which leads back to Siegel zeros. Okay, any way of circumventing that? Avoid, so if you know that there's a bad Siegel 0 that you want to avoid, maybe you can then try to only sum over numbers here that don't have a prime factor coming from that bad modulus, and then all the characters that you have will avoid that prime number, right? And then you can never have a Siegel 0 problem. Okay? So another way to say it is that, for example, take a simple case here. What if Q between capital Q and twice capital Q is restricted to prime numbers? In some ways, it's kind of artificial because in situations where we want to go beyond the Bombieri-Vinogradov theorem, it's precisely the opposite of prime numbers that you want to consider, like smooth numbers, all of whose prime factors are small, like Emmanuel explained, which is the content of Zhang's theorem, the original breakthrough. But if you started out with primes here, then passing to primitive characters is not a big deal because almost all the characters modulo p are going to be primitive characters, except for the principal character, which you've taken out here in the main term anyway, right? So another exercise for you is to go through the Bombieri-Vinogradov argument, pretend that you had a sum over primes, and then see if you can get better error terms than what we proved in Bombieri-Vinogradov here. Does that make sense? Okay. And then a variant of this is what Zeb mentioned. You can, so these Siegel zeros are rare, so pick a Siegel zero modulus. Let's pretend that there's only one of them, right? For all practical reasons, you can assume something like that. Okay, Q naught, and then take a prime P. Let's say P naught, maybe large, dividing Q naught, right? And then you can now sum over all Q between Q and twice capital Q, provided P naught does not divide Q. And then do the same thing. The max over all progressions of primes in this arithmetic progression. Okay? Whenever you decompose that into characters, all the moduli that you get of the primitive characters will be moduli not divisible by this prime P naught. Okay? And therefore, you can never get the bad Siegel zero modulus Q naught as one of the characters that you're considering. Okay. And then this is a trick to avoid Siegel zeros. Okay, so the upshot of all this is that in the proof, you see Siegel's theorem being used somewhere, which is ineffective, but then there are ways in which you can try to avoid this ineffectivity, either by starting out with a situation where you avoid Siegel zeros initially, right, by summing over some subset of primes, or, in the way I stated it here, just deal with the Siegel zero that might exist to one modulus, write down the actual main term in that case, and then see what you get when you carry it out. Right? And then you can use some kind of very naive, explicit effective bound for Siegel zeros, given by, class number is always at least one kind of argument. And then you can use that and still gain some result which is going to be effective. Okay? So this is maybe a technical remark, but it might be useful to you as you go on. So a priori, the Bombieri-Vinogradov theorem, as we've done, is ineffective, but there are ways in which you can circumvent that. And there are also ways in which you can modify the problem, so you might get a slightly stronger result, if that's necessary. So that's everything for Bombieri-Vinogradov. I still have maybe 15, 20 minutes left, so I will say a little bit about the exponential sum that you can form with primes, for which much of the techniques that we've discussed will apply and give you some nice results. So maybe I should keep this board visible for now. Oh, maybe I should tell you one more thing about this kind of identity, right? And Emmanuel will tell you more about these kinds of identities as well in his talk. We did this in some ad hoc way, but there are any number of ways in which you could write this identity. So if I didn't want to think about this, subtracting this first thing and then adding back and worrying about how exactly I did it, so here's another mindless way in which I could have done the same kind of expression. So I could write this as 1 minus zeta m plus zeta m, and then square this, if you like, right? And then multiply everything out, so you get minus zeta primed over zeta plus and then 2 copies of this. So 2, if I multiply zeta m by zeta primed over zeta, I get minus zeta primed m, and then times 1 minus zeta m. And then the last one will be plus zeta of s squared, m of s squared. Right? Now, okay, or let's, so maybe these 2 things are actually the same as that. Is that right? Okay. So minus 2 zeta prime times m plus 2 zeta zeta primed m squared minus that. So maybe, right? Yeah. And again, you can see that that this object is like a type 2 sum. These are all larger than m. Okay. So maybe think of it as one guy which is larger than m times the primes, but it's still going to be something larger than m when I multiply by a prime. So this is like a type 2 sum. And these I can kind of think of as type 1 sums. This parameter is small. This is an object that I understand, zeta primed, right? The coefficients are just log. And therefore, this gives me basically just a type 1 sum. What about this? This too, I claim, should be thought of as like a type 1 sum, okay? Because I can, this is a small guy. So these coefficients are going up to a large one, right? And then you can use the hyperbola method here. Or another way to say it is that these coefficients are like divisor functions, or basically the log of the divisor function in Emmanuel's notation, right? So, so again, you can think of this as a type 1 sum, where you have to understand something like the divisor function multiplied by a character, and what Emmanuel talked about the last lecture was the divisor function multiplied by an exponential sum, and then you can understand things about that. Okay, so now you can see that you can generalize this any way you like. Maybe you can put some other power here, or you can multiply a bunch of these things together, right? And in this way, you can arrive at many kinds of identities of this type, expressing primes or some related sum in terms of functions like divisor functions or generalizations of the divisor functions. This is also one reason why this exponent of distribution for the k divisor function is a useful thing to understand. If you understand things about exponent for divisor functions, by identities of this type, you can go back to understanding things about primes in suitable situations. Okay, so 2 points. So divisor functions are useful too, and also these identities are not special. Essentially, you can write down any number of identities that you want of that flavor. Okay. Now let me get back to the last application of this. Maybe I'll just sketch it a little bit. So maybe later this afternoon, I think you will have a presentation on the circle method or about trying to do the ternary Goldbach problem of writing odd numbers as sums of 3 primes. To understand the ternary Goldbach problem, it's useful to understand prime counting functions, not with characters which we needed for Bombieri-Vinogradov, but with some kind of exponential oscillating function like E of n alpha. Okay, so here if you can think of alpha as being some number in R mod z, it's measuring. So one thing you can see is that if alpha is close to a rational number a over q, with small denominator q, then this is measuring the equidistribution of primes in arithmetic progressions, right? But on the other hand, the primes are not completely equidistributed in all the arithmetic progressions. The progressions have to have, starting point co-prime to q. Okay, So the prime number theorem in arithmetic progressions would say that if you wanted to look at the sum n up to x lambda n e of a n over q, you might expect this to be very closely approximately something like mu of q times x over phi q. We did this kind of calculation in using the large sieve to give a version of the Brun-Titchmarsh theorem, right? At least if q is very small. So therefore, you don't expect to gain any cancellation in this exponential sum if q is very small. For example, if q is 7, there's not going to be much cancellation in this sum. Now, another way in which you won't get cancellation is that if q is very big, so let me write it as E of n divided by, let's say, the floor of x, right? So again, I don't expect to get any cancellation. This is on the scale of x, right? Because this term here, or maybe I should put a 2 here just to be safe, right? This guy is not oscillating much at all, so it's usually pointing in the same direction, and they all add up to give you something of size x, right? So if alpha is close to a over q, then I don't expect any cancellation if q is very small, or if q is very small, or if q is close to x. Right? In other ranges, you do expect that this sum will mostly cancel out. So here's another example for you to think about. What if alpha is, say, the golden ratio? Right? It would be a good exercise to work out explicitly for the golden ratio what kind of bound you can prove for the sum over primes. Okay? So the golden ratio has a property that if you write down a rational approximation to it, right, it will be usually pretty bad as a rational approximation, because the continued fraction looks like 1 plus 1 over 1 plus 1 over 1 plus 1 over 1, and so on. Okay, now how do we bound exponential sums of this type? We can use the same methods that we've been discussing here. Let's pretend that instead of this situation, lambda n, e n alpha, let's pretend that I can convert it to a problem about bilinear forms, and then I have some situation here like maybe m is of size m and n is of size n. Maybe I have some coefficients alpha m, beta n, and then e of too many alphas, okay? So am bn, e of alpha mn. Right? So basically, you can use the same identity that we had in our proof of Bombieri-Vinogradov, and just look at I'm just looking at the type 2 sums. You'll have to do something similar for the type 1 sums that arise here. Okay? So previously we used the large sieve. What should I do here? Well, I can just, the only thing I can do here is to use Cauchy's inequality. Okay? So let me bound this by the sum over m of size m, 1 to the half. So I'm going to use Cauchy's inequality with, maybe I should have taken the am squared here. And then inside I would have a sum over m of size m, I have? So this, let's say the AMs are usually of size 1, maybe give or take some logs. So this is roughly like square root of m. And then what do I have here? If I expand this sum over n out, I get a sum over two variables n1 and n2, some bn1, bn2. And then I have a sum over m of size m. And then the whole thing square rooted. Maybe this will be with a complex conjugate sign. Is that okay? So now here, you see the advantage that I have gained is in using Cauchy-Schwarz is that I had two variables, a of m and b of n, both of which were kind of essentially arbitrary functions or arbitrary numbers, right? I didn't know anything about a and b, okay? But once I use Cauchy's inequality, what I now have is a sum over m where the unknown quantities a of m have been replaced by just the number 1, right? Which is a big advantage. So this again was a kind of principle which we saw in the proof of the large sieve. When we went to the dual form of the large sieve, we basically had to evaluate a sum of this type, which is just a geometric progression, so it's easy to evaluate, easy to estimate. So the inner sum over m is going to be bounded by so let's just put b of n1 squared plus n2 squared, but let me just keep one of the n1s by symmetry. Okay? And then what I have here is a sum over m, which I can replace by the minimum of, well, there are at most m terms, so I only have to take, I always have an upper bound of m. And then this is a geometric progression with common ratio e of alpha times n1 minus n2. So when I proceed from there, I get 1 over the distance from the nearest integer of alpha times n1 minus n2. And then the square root of all of this. Okay? So now how do I evaluate this? Well, pretend that alpha is just the same as a over q. Maybe it's a over q plus a very small amount, right? By Dirichlet's theorem, I can always assume that there is an a over q with alpha minus a over q being bounded by 1 over q squared. Right? And then, so, but let's pretend that it's a over q. Then what I have here is something like 1 over the distance from the nearest integer of a times n1 minus n2 over q. Right? So there's a number of cases to deal with. If, say, n1 is congruent to n2 mod q, you would use the bound of m. Okay? Otherwise, maybe even if n1 and n2 differ by the multiplicative inverse of a mod q, then this one might be of size q, and maybe q would be bigger than m, and then you have to figure out which one to use. Okay? So an exercise would be to figure out, would be to say, would be that for about q over m plus 1 choices of n1 minus n2 mod q, right? This one could be the choice where n1 minus n2 is 0 mod q, okay? Where it's clearly better for me to use this bound m. Okay? For these choices, for these many choices, I would use the bound m. For the remaining choices, I would use the other one. So show that m is the smaller of the two bounds. For other choices, use the second bound. Okay. So I'm kind of sketching this more rapidly than usual, but you can fill in all the details. And so let's pretend that it's just this q over m plus 1 that matters. So then what you would get would be the bound, so there's a root m throughout, and then a sum over n1, n2. So n1 minus n2 mod q has about, let's say, is fixed in some number of ways, right? In this q over m plus 1 ways. And then there's an m times q over m plus 1. And then everything's square rooted. Okay, and what this means is that I can fix n1. There's kind of n ways to do it. And then if I fix n1, then the number of choices for n2 is roughly n divided by q, plus 1 maybe, right? So it's this times n over q plus 1 times m times q plus m, all of this to the 1/2. Okay, so forgetting some powers of log that you should work out. So when the smoke clears, this is going to be a square root of mm, and then a square root of q plus m, square root of q plus n, from here and there, and then divided by a square root of q. Okay, up to powers of log. And then you can see that this will be of the right flavor. I can bound this numerator. So bound this by root q plus root m, bound this by root q plus root n. When you multiply out, you get q plus root q times root m plus root n plus square root of mn. Okay, and then mn, the product of these guys, like in our usual way, is roughly of size x, at most of size x. So if I replace this by x, then the first term will be root x times square root of q. And then the second terms here, the root q will cancel out. And then I get x divided by square root of m plus x divided by square root of m plus, so that's from this. And then the last term, these two guys give me something of size x divided by square root of q. Apart from powers of log. Okay? And you can see that this is a good bound. It's capturing the flavor of not getting cancellation if q is very small or q is very large. If q is very small, this term is big, and you don't have much cancellation. If q is very big, close to x, this term is very big, and you don't get any cancellation, right? Otherwise, you have a bilinear form, and we know that in a bilinear form, like we did in Bombieri-Vinogradov, you save something provided both of the variables in your bilinear form are suitably big. If one of them is small and the other is big, you don't gain anything, but otherwise you gain, the minimum, the maximum of 1 over square root of m and 1 over square root of m. Right? So this is exactly the same as the argument using the large sieve in the proof of Bombieri-Vinogradov. And as you can imagine, you are free to choose m and n to be like a power of x, maybe like x to the 1/10. Right? And then you'd have saved, so the middle two terms will just disappear. You'll get something like x to the 0.95, let's say. And then what you've established is that for this kind of exponential sum, you get very considerable cancellation unless q is very small or unless q is very big. Okay? And then go back to this example and work out that if you take alpha to be something like the golden ratio, you will always be able to find an approximation to the golden ratio of the form a over q, in which q is neither very small nor very large compared to x. Right? The golden ratio has approximations, very good approximations, of basically every size that you like. And therefore, you should be able to get a good bound for primes counted with e of n times the golden ratio. Okay? All right. Thank you very much. Questions?
Any questions for Sam? Then if not, then let's take a 5 minute break and then we'll continue with the